Hello everyone, I'm Dejo Falk, and I will be presenting on my project demo results with my project of Can No Reference Image Quality Assessment Change How We Assess Images? With this presentation, I will be going over the results of my project and show all the steps that led to this result. First, I will go into an introduction of my project and the objectives that we will be looking at with this project. With this project, I have focused on image quality assessment, which involves using machine learning models to measure the image quality of images by looking at different distortions of the images that models are looking at. Once the model is trained and during testing, the model produces a numerical score that reflects the perceived image quality. In particular, with my project, I've been looking at no reference image quality assessment, which means that these computer models are providing scores to images without having the non-distorted reference image to refer back to when scoring image quality. The model I will be using in the project is based on the paper I have used as the basis for my project. That paper being Rank IQA, Learning from Rankings for No Reference Image Quality Assessment. This paper has been trained and tested on the most popular image quality assessment datasets, which are the original live dataset and the TID 2013 dataset, which makes the model very good for reusability and testing on other datasets. Because of this, I will be training this model on a new dataset. Testing this model on a new dataset. This dataset is the Live in the Wild Quality Challenge database that was created by the Laboratory for Image and Video Engineering at the University of Texas at Austin. Because previous image quality datasets are specifically tailored for image quality assessment models, this new dataset is designed to give more of a natural in the world feel to the images, so that none of the images are artificially distorted, which is very rare in image quality datasets up until this point. So moving on to the objectives of the project. The first objective of the project is to evaluate the testing results of the machine learning model we will be using with this new dataset. Looking at the model that we will be converting, we'll be looking at the results from the original paper, and I'll also run this model on my own computer to make sure I get results that are more recent and comparative for testing. And I'll also be able to learn and work with the metrics that are used in testing image quality assessment models, which is very important if I were to work with more image quality assessment datasets in the future. The second objective of this project is to see how the result of this model compares to the results of the original datasets it was trained and tested on. Of course, the results will be worse because the model isn't trained on this specific looking data, but it is important to see how worse this new dataset is. This is because this will tell me and other researchers about how well do older models work on newer datasets. That's a very important thing that I'll be trying to figure out with this project. But this is important because when talking about my third objective, it is to determine how models should be created and what researchers should have in mind when trying to sort of future-proof these models. When new datasets are being created, hopefully this project could help determine which decision is better between creating a new model that fits the new dataset better or using older models that can be used to still train and test these new datasets. But before getting into more detail, I want to show a few images from this new dataset that can kind of show what is different about this dataset. As you can see, the images on the left and right are the same, but with much different image quality. However, what makes these images and datasets cool is that the images give more of a real-world experience, and these images provide the models with more realistic images that you would see in the production in the real world. And these images that might need to be assessed and not just images that are tailored specifically for research and training. Before we can start the project, however, we need to get to the dataset and all the pre-processing needed to be inputted into the model. So when downloading an image quality dataset, it usually comes in some sort of format that you see in the upper left image. This photo is the new dataset I'll be using, but both the original Live and TID 2013 datasets are the same way, where they have the images in one or multiple folders in the MOS file. MOS stands for Mean Opinion Score, which is the subjective quality measurement that represents the average opinion of a group of human observers who rated the quality of the images. This file comes in every dataset I've used, but the problem is that um, the file comes in a .mat format or .mat, which you can open in MATLAB or Microsoft's Access database, which both of these I don't have and had trouble opening it when I did try to. Because of this, I use Python to get the MOS for each image and create a text file that has the image file path and the MOS score associated with that image. So in the lower left, you can see the script I used to get this. I loaded the .mat file, and got the MOS and image path, and then did some formatting to make sure the file path is correct. And with the MOS I created, the file you see on the right. This is all of the image file paths and the mean MOS associated with them in a readable format for the model to be able to read and understand. With the pre-processing and examples of images done, I can now go into more detail about the model I will be using for this project and the steps to get to the results with the dataset, this new dataset. In the original project and paper, there are 4 models that were used for training and testing. 2 of these models were used with the ranking datasets, and the other 2 were used to train and test the 2 original IQA datasets. Because I am using an image quality dataset, I will only be working with the fine-tuned models. However, before I use these models, I wanted to do a very important change. All of these models that were used in the original project were created in the CAFE framework. Although CAFE is popular in the deep learning community, it has a little more complicated understanding and installation to be able to run, and with my time constraints, I thought that converting these CAFE models to PyTorch would allow me to work with models I'm more comfortable with. But it will also allow me to see the process of changing models from one framework to another and see how easy or complicated that can be. Now let's go into talk more about the process of changing the frameworks and the challenges that accompany that. So, when converting a model from one framework to another, it took more steps than I expected, and it was a really eye-opening experience. So, at first, when working with the CAFE framework, I needed to obtain the weights of the model and make sure everything is available to do the conversion using the GitHub repository below. This is where the main problem came up because I actually had to go deeper into the model and repository. It go specifically into layers to get everything that was needed for the conversion. Once I found the weights and everything needed to input into this converter, it outputted a .pt file, which is what I was looking for each of the 4 models that were originally created in the original paper. The documentation of the original model was lacking when looking for weights and specifications of the model, but I kind of understood that because this project wasn't made to be converted to PyTorch because Cafe is pretty popular in upon itself. It has shown me that it might have been better to just stay with the original framework of the model, or also maybe using a pre-trained general model in PyTorch and then training that model to be similar to the original model from the authors. Luckily, later than I expected, I did get models that were available for testing with the datasets. So now to move on to the testing with the original datasets first. Before I start with going into detail about my results, I want to talk about the two metrics that are outputted from the model and describe what they mean. So to first talk about PLCC, which stands for Pearson Linear Correlation Coefficient. This is a statistical measure that quantifies the linear relations between two variables. In this case, the predicted quality scores from the model and the human observers, that is the MOS score. These are the two variables that the PLCC represents. And then the second output is the, I'll call it SROC score, which stands for Spearman's Rank Order Correlation Coefficient. This score is often used to assess the monotonic relationship between the predicted scores and the MOS score. But this score is less sensitive to outliers than the PLCC, and is more useful when the relationship between the two variables is expected to be monotonic, but not necessarily linear. Both scores are numerical values between 1 to -1, and this means that the closer the score is to 1, the closer the predicted score is to the human perception. And this is what you're looking for. You want the model to be as close to the human eye as possible when it comes down to image quality data sets. So now that we have the metrics explained, you can see that both of these data sets have very good scores. This means that these models, when testing on these two data sets, are predicting very well the distortions in the image quality scores. The live data set has higher scores, but the scores from the TID 2013 are also good. As you can see with the live data set, the PLCC and I misspelled it, but SROCC table on the live side is very close, while on the TID 2013 it's a little bigger gap between the two scores. So moving on to this new data set. The first problem I noticed immediately when doing testing is actually that I had to change a bit of the code to make it so that the models understood the .jpeg extension, because the previous datasets were .bitmap extensions. Of course, this is not something I expected to be a problem, because to me they are all images at the end of the day. But luckily, it was a simple fix. So after the metrics were outputted, you can see that the margins between the MOS and predicted value from the model on the left were much larger than the two previous data sets. This is the first thing that stood out to me. But this makes sense when looking at the PLCC and SROCC scores, because the other data sets were used in training, but the scores were still above 0, which is good. And this does make it so there is room for improvement, but it's not so bad that the model needs dramatic changes, which is something I was kind of expecting at first. But these two scores were much lower than the previous test. So, I'll be going through the conclusion of my project by the objectives I stated for my project at the beginning of the presentation. With objective number 1, I think that my results provided me with good insight about the model and how well it can support potential newer datasets. Of course, it is always helpful to test models with newer datasets, but if the results aren't helpful, it might be better to just develop new models. Going on to objection number 2, the results from this project were expected, but I did expect the SROC and PLCC to be a little higher with this new dataset. At the end of the day, it still is an image quality assessment dataset, so I was expecting maybe it to be about a tenth higher. To me, for objective number 3, after doing this testing, I do think that models should be more general instead of more specific with the training, because this limits in which ways the model can be used in production, specifically for the future. If you focus too much on the training of a specific data set, you might make it so that this model, what people in the community like to call overfitting, you might make it so that this model is very good on that training data set, but to work with other data sets, it's not that good. And with image quality assessment, it's kind of important because you're not just testing on one data set. It's a lot of data sets to prove that this model is better than the rest. I do think that researchers should make sure that the models, of course, are the best for the research they are focusing on. But I think it would be irresponsible for these researchers to not think about the future of the research focus they are working on. If they can plan, maybe it doesn't have to be long, but a few years ahead, and think about what their focus is going towards, if they could make a model that also helps that, I think it would be better than a more specific model for right now. So lastly, I wanted to go over some of the future steps that this project could take on with more time, but also things I'm interested in from working on this project. First thing is, when working with this specific paper, I do think it would be interesting to learn more about the ranking part of this paper, since I wasn't really able to use it for my project, but also how they expect to use this architecture in the real world. This project has also made me very interested in image quality assessment, especially because I had never heard of it before this semester. But I do think it is something that is very important with how much more the digital the world is becoming. With this, it would be cool to learn more about how these image quality assessment models have real world impacts and how these models are used in the real world. This could also help me understand how to better develop these models in the future. And then finally, with working with image quality assessment datasets, I think it would be cool to learn how these datasets are made and how specifically the MOS scores are gained and how human observers are brought into the research. This is something that, of course, these databases don't put out when they're putting out these their databases, but it would be cool to learn more about like how from the beginning of these humans just looking at images and scoring them can lead all the way to the end product of this model. And this is the end of the presentation. Thank you very much.